Okay, I'll start the presentation now. So welcome everybody to our SBN workshop series, the first one in the series. And today's topic is actually on building enclosures. So I'm your presenter, Bobby. I am a currently graduate student studying with the emphasis on building science. So I know a little bit about more of this. And so before I actually talk about the actual content for today, I'd like to remind everybody who's attending this or watching this recording on their own pace, that is recommended to everyone attending the workshop to attend all this workshop in the series, because we have a lot of connection in those workshops, and the actual content themselves will actually carry on to the later ones. And for the later workshops that we host, especially the coming two, that's HVAC and I think passive files and building orientation, we all have activities at the very end that you can participate, and actually sort of it's recommended that you have a prior knowledge of the previous workshop. So if we lay the groundworks today in this particular workshop, and we have a little concept about sustainability in general, in the later workshop, it'll be easier for you to understand and see the connection throughout these workshops. So without further ado, let's begin. So today's topic is on building enclosures. Probably a lot of people already know what building enclosures are, but these are actually very common thing that we actually see every day. Maybe we don't notice it, but it's around us since all the time if we live in the building. So basically the walls that we see, right, the exterior walls that we see, they are the major part of our building enclosures. So there are in total four main components to our building enclosure. If you can think of the building as like a box, and as a box we have 6 sides and 3 general directions. So basically the sides and the top and the bottom, right? So it's the same thing for a building, that we have a roof system, that's our top of the box. And we also have the sides, which is the wall systems. And also the bottom, that is our base floor systems. And maybe a lot of you are wondering why that we have like above grade wall systems and below grade wall systems separated as 2 different systems or 2 different components within our umbrella of building enclosure. That is because we treat those wall systems quite differently, because they are dealing with different environmental conditions. If we think about wall systems, they are basically environmental separators that separates us from the outside or the outdoor environment, that provides us with human comfort, maybe keep us warm or cool in the summer. So for the above grade wall systems, they're dealing with outdoor air that fluctuate a lot, and depending on the season, the outdoor temperature can vary a lot, especially for the climate like us, right? But for the below grade systems or below grade wall systems, they're mainly adjacent to the underground soil, which doesn't fluctuate that much in terms of temperature. And so you can think of the soil or the underground structure as sort of a damper. Basically, it is not going to have so much of a difference in terms of diurnal temperature variation or seasonal temperature variations. That's why we build these 2 components quite differently, and we use quite different methods to design our wall systems for these 2 different locations. And that is precisely why we have to separate these 2 out. And for the above grade wall systems, we often include the windows, which we call fenestrations, and the doors for this whole system. And as you can see on the right picture showing on the slide, the gray area are all the enclosure elements that we have for this particular building. And for the inside spaces or the partition walls, we don't count them as our building enclosure, because they are not really adjacent or connected to the outdoor environment. because if you stay indoor, the different rooms will have the same temperature if we're in a thermal equilibrium. That means there's really little heat transfer or little interactions between the internal partition walls. That's why we don't count them as our building enclosure. Same thing as the outdoor patio as seen over here, because we don't use that. We don't live in the patio space. Maybe we go out once a while, but we don't really spend a lot of time there. That's why it doesn't count as our building outer shell. It is something that's always outside, and we don't need to condition it. We don't need to heat it or cool it. That's why we don't count it as part of our building enclosure. And some of the other term, actually the other term that we use very often for building enclosure is called building envelope. It's dealing with essentially the same thing. It's just that sometimes we call it envelope, sometimes we call it enclosure. So why do we talk about building enclosures, and why do we put it as the first one in the workshop series? There has to be a reason. The main reason is that it really ties into a lot of things that we deal with later on, and it has a lot of internal relationship that we would like to discuss or investigate. That's basically very crucial for our goal to have a sustainable building. And for sustainable buildings, we need to consider the energy usage of the building, how to make the building actually energy efficient. And if you look at the energy mix pie chart showing on the slide, that the majority of energy used in a building is attributed to process heating and other equipment, so maybe, but the majority is process heating, especially for a cold climate like Canada, right? We really need a lot of heating energy to be able to maintain a thermal or a comfortable temperature indoor. That is why we really need to design our enclosure efficiently or in a smart way that can minimize this energy usage. So there are two main relationships that I would like you guys to think about beforehand. That is, how do we balance human comfort and energy use? And also, how do we balance indoor air quality and energy use? So let's talk about human comfort and energy use first. Right off the bat, what is human comfort, right? It's not just some simple thermal comfort, which we see, we want a temperature of 23 degrees Celsius indoors to keep us feel comfortable. But that's just thermal comfort. We as humans, we have a lot of demands. Maybe we don't say it, but we actually inherently do need a lot of demands. And these demands include, relative humidity. We don't want the space to be too moist or too dry. It's gonna, either let us sweat a lot or let our skin gets dry. And other concerns as well. You don't want the space to have too loud or have such a high speed of air transfer that sort of just give you a sense of draft. So these are the considerations that we need to incorporate to our design when we design our enclosures. So if you look at the lower left picture showing on the slide, so if you see the human comfort as the middle part, but we have to have all the other factors considered in order to reach that human comfort. We have humidity, right? We want to have, as I mentioned, a relative humidity that's comfortable, that's just right. For different seasons, it can fluctuate the number. And for airspeed, maybe a lot of time we don't notice it because our space or the building that we live in already has considered these factors, so we don't notice the airspeed. But actually, if you think about a poorly designed building, right, has sort of the air intake or the air diffusers right in front of your working area. So when the heater turns on or the cooler turns on, it just have a sense of sort of like air that's blowing onto your face, which is not good, right? I see one is joining. Wait. Hi there. Can you hear me? If you can hear me, just type in the chat so I can know. Yeah, I'll assume that you can hear me because I already started the presentation. You can have the recording of the presentation afterwards, so you don't miss out anything, right? But because the time constraint, I gotta go on because we only have an hour for this. So I'll continue to talk about what I've been talking about. So as I was talking about human comfort and energy use within the umbrella of sustainable building and building enclosures. So we don't want to have an airspeed that's going to bother us or let us feel a sense of draft. The air blowing onto our face is going to cause us to feel uncomfortable, right? And air temperature and radiant temperature, these are the two temperatures that we feel on our skin every day, right? We want to maintain that to a sound level that we don't feel too hot or too cold. And maybe air temperature is easier to understand because it's basically the air that surrounds us. It's going to have a certain temperature, and that temperature is going to translate to us either via convection or conduction, right? But as radiant temperature, sometimes it's a little vague to understand because a lot of objects, even though they are not very hot, they're going to emit radiant energy. And that radiant temperature basically comes off our equipment, our internal furnishings, even the sunlight. These are all the temperature, radiant temperatures are going to affect us. It's going to let us feel either hotter or cooler, right? So these two temperatures together, we need to consider them to be at an optimal level so that we actually feel comfortable. And the last two factors are actually dependent on us as occupants, because the metabolic rate and the clothing insulation or the clothing level that we have is entirely up to us, right? If we sit, now we're gonna generate a certain amount of energy. But if we do housework or do workout inside of a space, that we obviously gonna generate more energy, and that's gonna demand the cooling system to turn on or less heating to be provided. So we need to design our building smartly so that these factors can all be considered when we are living in the space, right? So that's human comfort, energy, and energy use, and how do we balance these two sides of the problem? The next relationship I would like you guys to actually investigate is indoor air quality, which we refer to IAQ, energy use. Because we spend the majority of our lives indoors, as shown on the slide, 90%, maybe higher for given the current situation of the pandemic, right? So we spend a lot of our time indoor, and because we spend so much time indoors, maybe even if the outer pollutant levels are higher than the indoors, but given the time scale that we spend, that in total we're gonna inhale probably more or higher levels of contaminants indoor. So indoor air quality is actually of very much a central importance for, if we consider human health into our human factor, right? So there are some common indoor air pollutants that we sort of experience when we're inside of a building enclosure. But it's not really an indoor air quality presentation, so I don't need to get into these details, but you just have to know that a lot of times these things are invisible, we don't see them, but we actually are breathing in these contaminants or some levels of these contaminants every day when we spend our time indoors. But what are the ways to actually control or to reduce these levels of contaminants? Well, one of the most effective ways is source control, because if you know the sources, you can control where it comes from. And if you eliminate the sources, then it will never generate that contaminant again. But the problem is a lot of times it's difficult to actually detect or trace down the sources of a particular contaminant, because the indoor air system is so complex and it's really hard to measure them. And sometimes even if we find the source of a particular contaminant, it is hard to eliminate the source, because if you see the paints they're gonna emit volatile organic compound, which we call VOCs. But can you have a house that doesn't have any paint, or so-called green paints or green organic paints that's marketed out there is not really that green or really that environmental friendly? They just market it that way. So there are really no ways to, or at least very good ways to control the sources. Therefore, we only can rely on, and generally we only rely on, ventilation rates. Basically, if you bring more outdoor fresh air into the space and you expel the used air inside the space to the outdoor, so you drive these air exchanges so that in the end, we're gonna have a much fresher or cleaner air, indoor air. So higher ventilation rate generally helps with indoor air quality. But there's always two sides of the coin, right? If you have a higher ventilation rate, generally you're gonna have more energy supplied to give or to provide that amount of ventilation rate. Because the majority of ventilation we provide to our space is through mechanical ventilation. Obviously, there's other ways it's possible. For example, there also is also natural ventilation. Basically refers to when you open your windows, you just let the air, outdoor air, come into our space naturally. And you also have air leakages, because we never can design our building to be perfectly sealed, right? There's always gonna be little leakage openings in and around the places, and that's gonna have air leaking through it and driving the air changes. Sometimes it's actually a good thing because there's actually air exchanges going on, right? So, but the majority of the ventilation we provide to a space is still through mechanical ventilation. Therefore, there's an energy penalty associated with that. So how do we really balance these two things? So the actually important takeaway here is that we can never design a building or a building enclosure that's going to be universally applicable to every situation, or it's perfect for every building. You just sort of copy paste this sort of practice to every building, then we're done for the day. It's not as simple as that, because context really matters. Depending on the location of the building, depending on the climate that you have, depending on different occupancy level and the targeted use of that building, is all gonna affect how we design the building enclosures accordingly, right? So there are really a lot of ways to see which way we use, right? We can use energy simulation, we can use building flush out to deal with indoor air quality. And we also can actively monitoring, like a CO2 monitor that monitors the CO2 level within a space, right? So these are all the examples of measures that we can take. And sometimes maybe we can have more operable windows that's closed or open on demand. Basically, you have a lot of human control over that operable window. And when it's closed, it's a very good window, and it doesn't let heat gain or heat loss through the window. Or when you can open it, when you feel like the space is too dry, or you feel the space is not really fresh, then you can open the windows accordingly. So there are some examples that we can use to control or to balance this sort of relationship between indoor air quality and energy use. So moving on, because the most common building enclosure elements that we see every day are sort of the walls the exterior walls that enclose our buildings, right? So so we take this as an example to talk about the wall assembly, because if you get this idea of wall assembly down, it can sort of be applied to other assembly as well. For roofs, for floors, they're essentially the same thing. You just imagine the wall being displaced in a different direction, right? So here we talk about the perfect wall assembly. Obviously, this is the ideal situation. If you don't think about the cost, you don't think about anything else, you don't think about structural things, you don't think about if the space permits you to have such a thick wall, then this wall is perfect for for almost any climate conditions. But this actually demonstrates what are the four main layers that we need to have for our building enclosures. or building enclosure elements to control different sets of parameters. So there are 4 main layers. If we see the first layer is rainwater control layer. So on the picture shown on the slide, maybe it's not very obvious to see, but I'll just say the left side is exterior, the right side is interior. So left side is in exterior space, so it has a direct contact with the outdoor air. That's why we have the brick veneer here, right? That's the outer aesthetics of the wall. And between after the brick veneer and this blue layer, here we have an empty space. Basically, it's just air, right? What does this layer do? So this is actually the rainwater control layer. Sometimes we call this a rain screen, or we call this a water barrier. Basically, if you think that if outside is raining and it's raining a lot of water through the brick veneers, because brick veneer, they are not really as rigid as you think. Sometimes they can have little openings and water just leaks through it, right? So this air sort of provides a space for the actual water to run down and to dry out to the outside. So that you can imagine the water gets in and you can stay on this layer and can drip out at the very end. So if you look really closely to the actual buildings, if they have like a brick veneer finishing, if you look at the bottom, there's always going to be a little gap that's allowing the water to dry out, to leaks, to actually come back out to the outdoor environment. So that's what this ring screen is used for. It prevents rainwater intrusion. And the blue part, this blue part is actually what we call exterior rigid insulation. So insulation material is actually the most important component within a wall to control our thermal transport, because we have insulation to impede the thermal transport of heat. That means, during the summers, the outdoor heat is hard to get in, and during the winter, the indoor heat is hard to get out, and which is both beneficial for us, right? And this outside exterior rigid insulation is same as insulation. It provides sort of a thermal resistance to the whole assembly, but it also, because it's rigid, the water is very hard to come through it. So it actually prevents the water from coming into the building enclosure or building assembly as well. But what if the water still makes a way through the building elements all the way behind the rigid insulation, like the black layer shown here? Maybe I'll change the color. This black line. And this black line is actually sort of the last line of defense for us to control the water. So say if you're really unfortunate, the water just kills through all that layers outside and gets to this layer. And this layer is the absolute last control, right? We have to control this water, otherwise we'll get into our later insulation parts or get into our indoor space, which is going to drive a lot of problems. A degradation to the wall assembly, maybe mold growth, right? We don't want those. And so this layer actually is a vapor impermeable and water impermeable layer that's going to stop the water and vapor from coming into our space. So it's a vapor control layer. Vapor control layer. We are often referred as vapor retarder or vapor barrier. That's gonna prevent the vapor transport across the wall assemblies. And because water is either in aqueous form or in gaseous form, right? So it can also be water or vapor. So we want to control both of them in order to make our assembly rigid. And we also want to control the air, because air is one of the most important way that our energy can be lost to the environment, because air itself can hold a lot of energy. And if we heat the space to a relatively comfortable temperature, but however, if you don't control the air movement, the air is gonna leak out or the outdoor air is gonna leak in, right? These are all gonna have associated energy penalties. So we also want an air control layer that's called an air barrier to control air leakage. So remember, sometimes a vapor barrier can be an air barrier as well, but sometimes they are two separate different materials. So depending on your choices or the cost, you may choose accordingly. And the lastly, as I mentioned, is the thermal control layer. So here we have the blue one, that's the rigid insulation. And we also have this one, which we call a bad insulation. Bad insulation. So it's often filled in within our structural studs. So you just fill these material within our wall. So if when you punch the wall, maybe if you can try it at home, you feel like it's kind of hollow. That's where it really plays the bad insulation. It's not like completely concrete. Otherwise, you will have really poor performance. Otherwise, unless you have such a thick wall, that's like called a mass wall structure, that's going to allow you to have the same thermal performance, but much thicker assembly. But that's the insulation control layer. And that's going to provide us with a certain amount of insulation that's going to keep the heat from getting in or the heat from escaping to the outside, right? So these are the four major layers of the wall assembly. As I talked about before, because if we want to consider these factors for all of the sides of the building, including the walls, the roofs, the slabs, then we need to do all these sort of similar ideas or apply these similar ideas to the other assembly as well. So you can think of you just put the wall either through this way or that way to become a new element, which we call slab and roof. So the idea is the same. We would want to have a vapor control layer, a water control layer, a thermal control layer, and probably a structural layer, or a structural layer. So if we see on the right picture, the lower right picture, we have the perfect roof and the perfect slab. They're essentially just a different orientation of a wall, because for the perfect roof, we have some material that's on the very top. We call it ballast, and that's actually little pebbles that's going to have a little weight to put on a certain layer in order for that layer to stay there. The wind doesn't blow it away. So it's protecting the filter fabric and the underlying control layers. The control layer here means the insulation, right? And underneath that, we have maybe vapor control layers and air control layers, and then the roof structure. And for the perfect slab, it's the other way around, because now the slab is on the top and you have control layer on the bottom. And now you have stones between your control layer and the actual earth or the soil underneath, right? So it's basically the same idea, but it's just applied to a different orientation or different direction. And it's worth mentioning that because we design all these enclosure elements pretty similarly, but we also need to ensure that the connection and transition between those elements needs to be taken care of or pay attention to. Because if you design a really good wall or a really good roof, but during the transition part on the corners of the building, if you don't consider them the same measures, you don't do the same practices, then it's gonna the heat or the water is gonna get in anyways, right? So you want to make sure these corners that are being taken care of. And because now we talked about how assemblies look like, we can now to actually evaluate how good is an enclosure assembly. So because we don't want to get into the mathematics and actual thermal dynamics of the building or the heat transfer, but we actually want to have a little bit of idea to how to measure the thermal capability of a enclosure element. So there are two common measurements. The first one is R value, which we call thermal resistance, or U value, which is at the reciprocal of the R value, 1/R value. So basically, R value measures how how good is a assembly to stop the heat transfer. And the U value measures how well does the assembly permit that heat transfer. So basically thermal resistance and thermal transmittance or thermal conductance. So if a wall assembly is really thermally capable, you will have a relatively high R value, but you will have a very low U value. So, and the vice versa, right? And the other measure that we commonly take is the vapor resistance, because like I said, not only do we need to consider the heat transfer, we also need to consider the vapor transfer as well, because you don't want the water or the vapor to get into our building assembly to degrade our building assemblies or to affect our human comfort, right? So we also have the measure of vapor resistance to measure the resistance to vapor transport. So if you take a look on the picture on the slide, as we can see, for the second row of wall assemblies, we have a U value displayed, right? From 1.7 to 1 to 0.6 to 0.45. The value is becoming smaller, right? Which means from left to right, the wall assemblies are getting better in terms of their thermal capabilities. So if you see on the leftmost example, it's just a brick, right? And a concrete. So it doesn't have any insulation. You just have an airspace between them. You can argue that's kind of like a insulation, but it's not really a good insulation. So then we move on to the rightmost example. It has an insulation material between the layers. That's causing it to have a much better heat resistance and a lower U value accordingly. So nowadays, if we want to have a 0.3 watts per meter square Kelvin of U value, we can do that by doing a lot of different combinations. We can put the insulation material between the concrete, still leave the airspace open. We can either put it between the two structure components, or we can have airspace and a little bit of insulation, or we can just have like a mass wall. We call a mass wall. Basically, like I said, it's gonna be a very thick and heavy wall, but you just utilize a lot of concrete because it's very thick. It's gonna perform perform the same as the other examples, right? So this is how we measure the thermal capability of a wall assembly. And we also want to avoid something that is in the industry that we don't want to ever do. That is called a vapor sandwich. It's not any normal sandwich we eat every day. It's just a vapor sandwich. What it means is that you don't want to have two vapor barriers in assembly, and in between you have a bunch of control elements, say like insulation or other air barriers or other structural elements. Because if you think about the vapor barriers, they are supposed to impede vapor transport, right? But what if the design is not perfect, or when you actually apply those layers to the site, the workers are not doing so with perfect practices? Maybe there's some leakages somewhere, right? There's always a chance for that vapor to get inside the building enclosure whatsoever. But if you have two layers that's sort of trapping this layer within this vapor within them, then once the vapor gets in, it's very hard to find its way out. It's not gonna be so smart and has a brain to find a way out through the same way that it came. So you don't want that to happen. So once the vapor gets in, it has nowhere to dry out to the outside world. And then the vapor just stays inside the assembly, sort of degrading that assembly element or damping that vapor, that insulation material, making the insulation ineffective. So we don't want to have vapor sandwiching. This is very important. So as see on the picture on the slide, we have a vapor profile. Basically means around here, we have our vapor control layer. Vapor control layer, right? And this layer, because only have one layer, the vapor either can come from the left or come from the right. but you will never have a problem with drying out, because once it comes in, you can always dry it back out to where it came, because there's no other vapor barriers stopping it from doing that. So we always want to keep a vapor profile that's open to the sides. So either the vapor comes in from the indoor space and can always dry out to the same direction, or the vapor comes in from the outdoor space and can always dry out towards the outside once the vapor is being dried out, right? So we also always wanted to maintain that, and we don't want to put two vapor barriers in the assembly. And now we talked about wall assemblies. And as I mentioned before, because fenestration, also known as windows, are also part of the of our wall assemblies. And because window is a special element, we need to actually pay actual attention to this, because it's completely different from the other components that we talked about, right? It's not a structural component sometimes, it's just glasses that we see through. So why do we have windows? Basically, when we have windows, we can see the outside world, we can see the landscape, we can see the scenery. This makes us feel better. You don't want to live in a building that has no windows. At least I personally don't want to live in them. But windows is very important. But windows are also very poor insulators. They are just glasses, right? They're very thin and they have very high thermal conductivity. That means just heat or can get in or get out very easily through windows. So in order to satisfy our demands, which we want to have windows, but also keeping them thermally capable, then we can introduce some type of high insulation or low U value windows. Basically double glaze or triple glaze. Double glaze means there are two glass panels, and triple glaze means there's three glass panels. And it's not really the glass panels, the additional glass panels, that makes them thermally capable. It's actually when you have a double glazed window, you can stick one air layer or a inner gas layer inside of these two, in between these two glass panels. And it's precisely these infill gas that provides us a thermal resistance associated with the windows. So, and in the case of triple glazed windows, then you can place two layers of air or inner gas in between these glass panels, which is gonna make the windows even more thermally capable, right? So that's how, because air is a really good insulator, and we don't want that gap to be very large as well, because you want the gap just thick enough to give it a relatively good volume there, but you don't want it to be too big in order for the air convection to happen, right? If you have such a big layer, the air convection can actually bring the heat from the bottom to the top in like a convective cell, and that's going to make your window perform worse. So that's how we modify the windows to make them thermally capable. And on top of that, we can also apply low E coatings, which we call low emissivity coatings, to the glass surfaces to reduce the radiative heat transfer. So if you look at the picture on the slide, I don't want to get too deep into the low E concept, but you can think of low E coating as some sort of a reflector, right? So the heat, summer heat, is reflected backwards, so that it doesn't have that sort of a lot of heat gain to our space during the summer that require more cooling. And during the winter, our indoor space is also gonna emit long wave radiation to the outdoor environment. And we don't want to have that, because we want to retain the heat within our indoor environment. And by having this low E coating, our indoor heat is also retained or reflected backwards in the winter. So that's the idea of low E coating. And again, because as I talked about, the importance of transitional elements, right? No matter how good you design your windows or doors, right? They can be super insulative or just carefully, perfectly designed. But if you don't take actual attention to the actual transitioning part, like the edges of the window, it's not going to have any, it's not going to work because the air leakage can still happen, and they're going to have thermal bridging effect, which is an effect where heat is going to transfer through the window frames that has a low thermal conductivity, and the heat's going to lose the outside anyways. So we need to have special attention to the edges of the window or doors, or the connection points between different enclosure elements to ensure that our design is continuous, right? So that's the two main parts: thermal leakage and thermal bridging. We want to avoid that by paying special attention to the edges and corners. And there are also a special type of windows, which we call operable windows. And why we just exclusively talk about operable windows here is because we want to tie this into the aforementioned air indoor quality side of our sustainable building, right? So there are some pros and cons about operable windows, because having an operable windows is kind of controversial, and it's really depending on the context that you have, you may apply them or don't. The pro side of the thing is that you really enable the natural ventilation. As I talked about before, if we don't want it to have mechanical ventilation to have such an energy usage, you maybe have operable windows to control the air movement while having no energy penalty, at least for the actual operation of this ventilation mechanism, right? You just open the window and the air comes in, and there's no energy associated with that. And it's good for the indoor air quality because it drives more air into the space, more air changes per hour, and it has a relatively easy human control, because whenever you feel hot, you feel you want to open the window, you can always do that, right? But the con side of the things, or the disadvantages of having operable windows, is that especially during extreme weathers, when the outside is either too hot or too cold, when you open the window, right, and that sort of cold air or hot air is going to get into our space, and it's going to demand our HVAC equipment to do more heating or cooling, right? So you really want to control that, by opening the window, maybe on a not so cold or not so cool day, and that maybe will work depending on the context. And also some people may argue that it's not safe because it's operable, and maybe somebody just can't get into your space by breaking out the window, but that's arguable, and it's not really important for our discussion today, but just let you know there is this point. So in summary, that our building enclosures, they're basically environmental separators, and they're directly responsible for the heat transfer and the vapor and water transfer between our enclosure or our space with the outdoor environment. And they dictate the building's hygrothermal performance, basically the thermal and the vapor and water side of the things. And we really don't have a universal solution to every building that we consider, because every building is designed differently and they are placed in different locations. And we really need to look at the building itself and maybe do an energy simulation and do a detailed hygrothermal analysis, try to mimic the situation and look ahead in the future, see whether this enclosure element is suited, or this assembly choice is going to be best suited for our situation. And lastly, as I always mention that, and I always stress that very important point, is that we have to have a continuous enclosure. Otherwise, what you do on the other elements, it won't matter, because the connection points are part of our enclosure, and it should be taken care of with the same level of care, right? Yeah, so that's the summary. And because we have 2 upcoming workshops, and I wanted to make some connections and maybe encourage you guys to go to the next 2 ones, because these ideas are not just standalone ideas, they are all interconnected in terms of getting a holistic view about sustainable buildings. So the design of building enclosures, as we talk about today, they really determine how we size our HVAC equipment, basically our cooling, central heating, or conditioning units, because if we have a very thermally capable enclosure, we don't need to have much heating or cooling, right? So that determines the HVAC equipment sizing. And the air tightness may also affect the desired ventilation rate. If we have a very airtight building, right? An airtight building, and it may sound very good because we don't have air leakages, we don't have energy penalty associated with energy with air leakages. But if we want to have the same air changes per hour for a building to ensure the same level of indoor air quality, now maybe we need to have more ventilation, mechanical ventilation rate, because we lose that part of air leakage rate as part of our ventilation. And also, maybe we want to consider the thermal performance of the enclosure that actually dictate the amount of cooling and heating loads required by an individual HVAC equipment. And also, because we talk about vapor transport and water transport, right? It also affects the air conditioning needs, like the humidifying and dehumidifying methods. So that's the connection to the upcoming workshops. So I encourage you guys all to attend the later ones, because that's the only way that you can have a holistic view on the entire topic. And you can take home with the holistic idea about, how do we consider a sustainable building and what kind of measures that we need to take in, considering the context of the things, and try to make this solution suitable to that particular type of building. And obviously today, only we have a certain amount of time. We're not going to cover everything there is about enclosures. So I here give you guys a little bit more resources where you can find more resources to look into the topic. So if you take courses within U of T, which is the most efficient way, that is you can take Civ 375 or 575, it's building science, and it really covers nearly everything I talked about today. And there's actually a course that specifically talk about design of building enclosures as Civ 578. And as I talk about indoor air quality a lot today, you can also, if you get into graduate studies, you can take the course Civ 1320, only available to undergrads. So actually Civ 375 and 575, they're the same course. Basically within the same course, you have two groups of people. One is for undergrad, one is for graduate. They have different syllabus, but they share the same sessions, basically. So you can obviously, if you're undergrad, you can take it for sure. And you can also take 500 level courses when you get to your final year. So it's the same anyway. Yeah, so there's also other courses which is Civ 576, which talk about sustainable buildings. And it's basically the same idea, but emphasis on green building standards and all that. And there are also a lot of useful web sources. As a link I given here is very useful, and it's not really like dry. The articles on this website is pretty interesting and has a lot of illustrations, so it's easier for you to understand. And if you wanted to get into really detailed stuff and technical, you can also look at the Canadian Building Digest. It's in the NRC archive. You can just search for it. As for the books, because the books are all pretty lengthy and they obviously talk about these topics more in depth. And here are the books that I recommend. And after maybe you look through all these resources, you will be for sure a building scientist. You will know everything. And it's enough for the day. And now, as we still have a little bit of time because we started at 6:10, yeah. So I think we can do a short activity, which I'll give you the link of Kahoot questions that I created. You can just join the room and test your knowledge on today's session, and maybe try some question out. Let me just find the Kahoot link. I'll type it in the chat. So there are 8 questions that you can do, and we can all do it together and compete, have a little competition. So try if you can open this link. It's just a play, you can play the link. Can everybody get into the room, or Does it ask you to have like a pin, game pin?
Yeah, we need a pin to get in.
Here's the game pin. Once you click that link, you'll ask you for the game pin, and you just type this in, and you're good to go. I'll wait till everybody gets in, and I'll start the quiz.
Yeah, we will need to see the screen as well to actually see the question.
Sorry, Rose, you were speaking. Sorry, I didn't turn on.
Yeah, we actually need to see your screen to actually see all the questions. On our phones, we just have the answers, like we pick the answers.
I haven't started them yet, because maybe
Yeah.
after I started them, you can see them.
Oh, no,
Let me see, how many people do we have here? 7. So there's supposed to be, 6 people. So I'm still waiting on some people to get in. Is everyone able to get into the link? I see 5 people now.
yeah, I think that's all.
Okay. Oh, one left. Okay, I'll start the thing, and tell me if you can see the questions. Okay, start. Can you see anything? Can you see questions?
Oh,
Yes?
yes.
Okay.
Yeah.
Yeah, you guys do the questions. All right. A lot of them got it right. Next one. Okay. Oh, okay. I'll talk about this a little more later. Next one. Oh, this one's a tie. Okay. So now I'm going to talk about the questions a little bit. See where you got it wrong. Okay, I actually have to share my screen for this. So congratulations to the double smiley face. You got the highest. And the Rose and Colin, right? Okay, let's see the questions and where we got it wrong. Okay, let me stop share this. Try to share my screen. Just hold on a minute. Let me see how to do that. Can everybody see my screen? Maybe you can.
Yeah.
Yeah, you can see it. All right. So the first question: which of the following windows has the best thermal performance? And it's triple glaze because I try to trick you on this because triple glaze plus low E without the leaky edges is supposed to be the best. But if you are leaky on the edges, as I talk about the transitional elements, they really do matter a lot. So you need to select the triple glazed one. And the next question, common in practice, we often avoid which of the following enclosure. I think nearly everybody got it right because we want to avoid vapor sandwiching. Sometimes we can install the insulation on the outside as rigid insulation, and it's applicable. And applying the ring screen to walls, we often do that because we want to control the water movement. And we also want installing the vapor barrier and air barrier, sometimes within the same assembly, because they control different elements, right? So it's vapor sandwiching. This one, we need to always work towards designing a perfectly airtight enclosure. A lot of people say it's true. Actually, it's false because whenever you see always, it's not gonna be true because perfectly airtight enclosure, as I say, it may be very good in terms of air leakages, but in terms of indoor air quality, it doesn't have any air leakages that provides us with air exchanges that's going to help us to improve the indoor air quality. So it's really like a balance. Sometimes you don't want to overdo it. And perhaps the easier way to say this, we can never design a perfectly airtight enclosure. It's not possible that we design that. So yeah, it's false. In enclosure designs, what's one trade-off between IAQ and energy? It's similar to the previous question because tighter envelope or tighter enclosure will lead to more ventilation needed to maintain the same air changes. And the air changes is a key factor that help us to improve our indoor air quality, right? And the other ones are sort of wrong because no trade-off is not possible. An operable window can increase thermal control, which is a win-win for both. It's a win-win for human control, or maybe for indoor air quality, but it can be a penalty for energy performance. And better IEQ is a result of higher thermal performance. It's not necessarily true. You can have it, but it's really a balance between those two things. And the next question, which of the following are a part of our building enclosures? I think I designed this question a little wrong because I thought you can select two answers, but it turns out you can only select one. But the correct answer are these two, so above grade exterior walls and windows and doors. So I think all of you got it right. Next question. So our office tower in downtown were constructed with single pane windows retrofitted with a double pane window, which lead to, so it doesn't help us see further, right? So it's not increased views, decreased daylight, it's not tainted windows, so it really doesn't do that. Increased thermal control, it's not really will we control the windows there, right? We don't have control over them. How do they transmit heat or something? It's only that it decreases our energy demand. Basically, less heat is escaped to the outside, less heat is coming into the environment, so we have less of energy demand for cooling and heating. So that's the essence of that question. Next one, the idea of designing turnkey vapor transfer is applied to everything, because not only just the above structures, because below ground we have groundwater, we have rainwater infiltration. We also need to consider that as well. And as well as for the window wall transitions, obviously transitions also matter a lot. The last question, generally speaking, below grade walls need less insulation. It is true, because generally speaking, because our underground soil is more temperature consistent throughout the year or day, it doesn't fluctuate as much as the outdoor air. So it generally doesn't need as much of air insulation material or insulation material in general. So yeah, that's the questions. And I think everybody had pretty solid understanding on those. So I'm going to stop sharing. Are there any other questions regarding the workshop today? Feel free to speak up or type it in the chat. Anybody has any questions? And I think, do you guys want the slides? Maybe I can share that with you guys as well if you want the slides. Maybe.
Yeah, that would be nice if we could. I missed like the first 40 to 50 minutes of the presentation. So yeah, that would be appreciated.
It's actually recording right now, because later on you can access the recording. You can see the previous part that you missed. It's all right. So yeah, okay. Hey Rose, how do we give them the PowerPoint or the document?
Yeah, we can put it on the SBN website. So we will put the recordings and the slides on there afterwards. So probably by this weekend or next week, we can put them up.
Yeah, so that's how you're gonna get the recordings and the slides. And if you don't have any other questions, then you can feel free to leave the session, and have a good night.
Thank you, Bobby. Thank you, Rose. Have a good night.
You're welcome. Okay, thank you.
Thank you for coming.